for some context and background about me, so as Ray suggested, my early career was getting my hands dirty, frontline maintenance. After a short period at university, I held various roles in power controls and in civil aerospace, and I'll be drawing on some of those experiences. I've got a research background in maintenance engineering, specifically with the application of machine learning to condition-based maintenance. And as Ray suggested, in recent years, I've been engaged in reliability engineering, teaching and research. So with reference to the presented figure, you'll be pleased to know around lunchtime it will not be death by PowerPoint. There is a single slide. I'm trying a new format today. So what I'd like to do is present challenges that have been presented to me over the years that I take no credit for. So in my role as an academic, I'm in a very privileged position to work across sector with many engineers in maintenance, and they identified challenges what I believe to fit well around these three themes. One of the things to be mindful of is, as Ray suggested, later on I'll be moving into potential solutions. I take full responsibility for those. Those are my ideas, but this is a collection of primary data gathered during my work in the last 15 years. So there's two insights really to this. First of all, supervising applied research. I'm very fortunate that a lot of my PhD students hold very senior positions in industry from across sector. A lot of experience, and I'm very interested in applied research. So that was one feed into the challenges that we'll discuss today. Usually in a part-time capacity over a 7-year period, but they can submit within 4 years. And it's a great opportunity to remain connected to industry. The other big piece, the other big part of my role is teaching professional development courses. So for those that don't know, professional development courses, specifically for maintenance engineers, again, we're targeting practitioners from across sector, usually small cohorts, in fact, probably smaller than we have here today. If we go beyond the 35 delegates in any face-to-face meeting, it can become quite challenging to manage the discussion and share experiences. Usually delivered by subject matter experts within university, but with industrial experience. And that could be people from the engineering community or indeed business schools. So we often deliver across a range of learning outcomes for engineers, but we don't just focus on the engineering. Some of the courses are closed, so they will be dedicated to a particular company. And of course, they will have their own unique challenges. Some of them are open, so I think they work incredibly well. There's often common themes around challenges that emerge, and there's sharing of experiences. During the pandemic, sadly, a lot of this was delivered by distance learning, but before the pandemic and starting again now, they're blended. So typically we'll have at least 1 or 2 weeks on a campus environment. And we'll be delivering taught material. And the really important piece is that we ask practitioners to go back and apply reflective practice. And that's essentially where these challenges came from, in addition to the research. So they reflect on the taught concepts. What do they mean to them? Provide evidence that they've made some progress, but identify future challenges. So that's the context. Let me get straight into, frame this around the 3 Ps, a very conventional way to present in this format around the process, plant, and people. Some might argue that plant's a little bit tired now. Maybe that should be technology, but doesn't roll off the tongue as well as the 3 Ps. So we'll stick with this framework for now. I think it's important to acknowledge that these challenges, that there are some dependencies, and there could be a debate about whether they actually fit within those categories. So they're not mutually exclusive. Let's start with digital asset data. Well, first of all, I think there's strong evidence to suggest that there's a real lack of standards. Over the years, I've had the privilege to develop international standards in asset management and maintenance engineering, and including ISO 55000, and the latest standards try and put a bit more detail into this, a little bit more thought around non-physical assets, digital data. But it's a standard, and it has to meet the needs of all, both internationally and cross-sector, and that can be a challenge. So I still think there is, well, evidence would suggest that there is a real lack of standards in this area. The other thing is, what data is in scope when it comes to digital asset data? I'm mindful in the room that there's a number of disciplines from sales, procurement, and engineering, so I'll try and avoid some techie speak, I'll try and avoid acronyms, and I think there's a lot in this. In fact, part of the challenge is working together across those communities rather than in the silos. So what data is in scope? Does that include design data? Should it include design data? Should it include reliability analysis, failure data, in fact, success data? With the onset of Industry 4.0, should it include condition monitoring data along process control data? Should it include sales data, procurement data? And I think that's really unclear. There's very few companies, in my experience, that really have a clear digital asset data strategy, or indeed any digital strategy at all. And I'm going to point to John at this point. John within RS is working on this very subject from a marketing perspective, and it was confirmed to John in a recent event that there is a real lack of strategy around this. One of the biggest challenges is understanding the value of digital data. There's a lot of debate at the moment that for some organizations, the value of the non-physical assets is now greater than the physical asset. But how do you put business value against a digital asset? And finally, spare a thought for small to medium-sized enterprises. Right now, there will be small operators in the UK that are dealing with an unplanned breakdown. They're stripping the machine down. They haven't got the parts. This evening, there'll be a tool maker that are making those parts, and hopefully it will be ready for some time tomorrow. So we need to keep this real. And when we talk about digital asset data to those operators, it's a difficult sell. So technology readiness. A lot of my work in professional development, in fact, was sponsored by an oil and gas major. And high-risk companies do a lot of good stuff with reliability engineering. A lot of the methods that we used are born out of the high-risk industries for good reason. They have very good processes around technology readiness, understanding how those technologies, what is their maturity. But sadly, after the major projects, when they're deployed to operations, it's not really well understood. It seems intuitive to suggest that if we change the duty or the load on assets, then maybe the performance that we had planned, the technology readiness is not the same. The technology readiness is lower. And from a maintenance perspective, we need to recognize that and manage it accordingly. Let me share with you some war stories. I think in an event like this, we should share some war stories that hopefully we can learn from. So there are examples in oil and gas where, can you believe, 30 years ago, people felt quite comfortable with subsea equipment in shallow water. But when we moved to deep water, they just assumed that the same kit would perform in the same way. Well, it doesn't. With a high pressure, high temperature well, there were lots of failures. And there's another example of how ready was that technology operating in that new environment. If you're not familiar with the oil and gas sector, I'd urge you to have a look at the AREDA database. It is an open format database. It's one of the best examples of how to collect field failure data, use it back into projects, and ultimately in maintenance engineering. The other thing to note is, I'm sure there are some in the room from maybe food and beverage that during the pandemic, their product lines, the demand for their product lines changed. And again, there was extra load on those machines, and they will not have behaved in the way that they did before. They need to be managed very differently. Disconnected communities. This must be the first time I've ever presented to professionals from sales, from procurement, and from different areas of the business. So what a great opportunity to talk about disconnected communities in terms of functional silos. One of the biggest challenges that we have in maintenance engineering is getting input during the design phase on major projects. This is a big challenge for any industry. Some industries are better than others. But how can the project teams that typically don't operate anything, maybe in their entire lifetime, be expected to understand good maintenance engineering and good strategies? When it comes to control engineering and maintenance, I think there's been a lot of progress in preparation for Industry 4.0 and many of the topics that we'll cover today. In fact, in the food industry, there's some great example where there are integrated teams. And now I'm going to touch on procurement, and there are some horror stories. So when it comes to procurement, maintenance, engineering, and procurement must work more closely together. There are two elements to downtime. One is an active repair time, the engineering piece, and then there's the non-active repair time. And when I would challenge practitioners, usually engineers, which one is greater? They will always say, or more than often say, oh, well, the non-active repair time. Okay, so as a group, where do you focus on? Well, we focus on the active repair time. So orders of magnitude greater. It could be hours for active repair time, days, weeks, and sometimes months for non-active. And the answer is, well, that's not my job. That's procurement, logistics, and support. So I think there has to be a better integrated approach going forward. We'll talk about some solutions later. Black box decision making. Rob is in the room and Francois, and they have a lot of experience in these areas. I first started my journey in machine learning over 20 years ago. And back then we were quite excited by the opportunity of handing over the decisions to machines. You know, that's okay, we can hand over these critical decisions to the machines. And even then, even now, I think maybe that's a little bit too ambitious. Rob and Francois might disagree, and we'll have that discussion with questions. One of the biggest challenges is, when it comes to supervised machine learning, we need to train them to understand individual failure modes in service if we do anything of any level of complexity. But the reality is, let's hope that we don't experience those failures in service. And therefore, we are unable to train the algorithms to recognize those signatures. So they can take some bedding in time. There are some solutions. Let's move on to plant and technology, life extension. There are many organizations right now, operators in the UK, that are managing assets that have exceeded their design life. I had the pleasure to supervise the chief engineer from one of the UK power stations, and that was his very job. His large rotating equipment had approached the 30-year target, and the replacement wasn't coming anytime soon. And so what do we do about that? What do we do around managing those life extensions? Often there's poorly defined life extension planning. So what is the strategy? How do we plan? How do we ensure that we meet the business need going forward in terms of life extension? And for many, it's just not an option to replace that kit anytime soon. It might be a political decision, internal politics, it might be CapEx constraints. So just get another one now is often not the answer. And sometimes, even if you have a 10-year window of preparation and planning, it may not be enough. Obsolescence, this for me is one of the biggest ones, and again there is another war story. So accepting that there are a lot of opportunities for the generation of, when it comes to operations facing the daunting prospect of maintaining equipment that is 30 years old or greater, and there are refineries that are much greater in terms of time, how can we be expected to support these assets? The microprocessors were from 2 or 3 generations ago. Industrial microprocessors continue to improve performance exponentially year on year. And access to earlier generation equipment is very difficult, and here's another war story. There are examples of operators right now sourcing used critical spares from a well-known online auction site, and that scares me. So remaining life, and when it comes to remaining life, let's talk about reliability. So reliability, I'm going to get a little bit techie if you'll allow me to spread my academic wings, is the probability of success for a given period of time, but as we've already established, it's dependent on a number of factors, including the environment that it operates in and the duty that it's subjected to. And so when we talk about remaining life, is it really possible to predict remaining life, long-term remaining life, for applications that are subjected to dynamic loading conditions? And to give you an example of a mobile phone and a battery, it will give you an indicator, and you may think it's okay for the day, but ultimately, if you're on the phone for 3 hours, the indicator drops very quickly. So in terms of working with other functions and departments, if we're doing long-term maintenance planning based on a remaining life model, let's be very careful. Let's be very careful that we don't make critical decisions where the duty might change and or the environment, and ultimately, when you thought you had 6 months to replace a part, now you've got 6 weeks, or in some cases, 6 days. So reliability and maintenance specifications. And again, a little bit technical here. So there are 2 governing parameters in my world. One is the mean time to failure, and one is the mean time to repair. They are used by most sectors. They are benchmarks of performance. They are targets, but they are flawed. They are fundamentally flawed. By their very nature, they are a mean. And there are examples of a particular failure in service where we go back to an OEM or a vendor or a machine builder and say, let's double the mean time to failure because we're going to be fine. And then between now and the next turnaround, the failure rates actually, the number of components failing, increase. So the mean time to failure is a very crude measure. We need to be mindful of that. Maintenance engineers don't seem to be consulted with regard to requirements for reliability and maintainability. Even worse, there are major projects in oil and gas, billions of dollars that are being signed off right now against a financial memorandum and a promise that they can deliver 85% availability in year 1, 90 in year 2, 95% in year 3, and they don't meet the targets. And the reason they don't meet the targets is because a lot of the predictions around mean time to failure and mean time to repair were unrealistic. They didn't consult the maintenance engineering community. That particular repair isn't 3 hours, it's 3 days. That makes a big difference on business performance. It is a relatively short presentation, I promise, so we're getting there. So let's touch on another subject of mine, a real active subject in both teaching and research, is human reliability. Thankfully, I'm looking around the room, thankfully, for most of us, there will be opportunities for the rest of our lifetimes. And that means that there are people in the loop. Okay, now if there are people in the loop in procurement, sales, in engineering design, in maintenance, unfortunately, under certain conditions, under certain error-producing conditions, humans actually perform terribly. We are very unreliable. So I've spent the last over 30 years focusing on the reliability of the machines, only to learn that actually if there are people in the loop going forward, maybe we need to be thinking about that as a system approach. I'm going to give you an example of the good and bad boss. This is the first time I've ever told this story, and I'm streaming online, and I'm thinking the bad boss might be online, so I've got to be careful. So I think we've all been in this position where we have a good boss. One of my first line managers was an incredibly inspiring, experienced engineer in maintenance, frontline maintenance. This particular individual would be incredibly supportive of college work, of writing up logbooks, could see when people were tired, would be working 3 hours overtime. That's enough, everybody go home. Let's start again tomorrow, you're fresh. Then there was another individual who I've probably got a lot to thank for. It's one of the reasons why I'm here, the bad boss that took over when the good boss retired. I don't care if you've got any plans this weekend, everybody's in. College work, do you really need to go to college tomorrow? Well, actually, I'd rather you didn't. Logbooks for your apprenticeship? No, thanks. And it was a terrible environment, really stressful. This particular individual would look over your shoulder during a maintenance operation and shout, hurry up. Let's get this thing fixed. What do you think that does to human performance? Not very good for human reliability. Competency. So when it comes to competency, I think there's a real shortage in skills in our particular discipline of maintenance engineering. Partly to blame is higher education. So most of the professionals I teach are on postgraduate courses. I'm not aware in the UK, I could be wrong, I'm an external examiner for quite a few universities, that we even teach maintenance engineering at undergraduate level. I'm also a non-executive director for an engineering training charity in the UK, my old apprenticeship school. And when I look at how they are treated by government and local councils, it's quite depressing. They rely on handouts from local companies. The apprenticeship levies have done very little to improve the situation, and a constant changing of training standards. My own son's just completed a maintenance engineering apprenticeship, and what a mess. I mean, in this case, he had to complete both standards in the transition, both standards, rather than the old or the new standard. Theory versus practice. Reliability engineering is underpinned by theory, and they're typically probabilistic techniques. This is where I normally liken it to predicting weather, but you lose all confidence at that point. So they're probabilistic techniques versus deterministic techniques. So when I see engineers talking about reliability to 3 decimal places, it's really meaningless. These methods are very strong relatively, not very strong absolutely. And here's the dilemma. For a reliability engineer to do any meaningful data analysis quantitatively, we need failure data. But if we do our job well, we don't have any failure data. That's a real dilemma to take away. Resourcing. This is normally a forbidden subject in education because we say lack of resources is a given, so tell us what your other problems are. But the reality is there are resourcing challenges. These methods that we've talked about require upfront investment in terms of analysis, time, expertise, but with the notion that longer term, there are longer term benefits with regard to the life cycle costing. The other thing I find really alarming on major projects is maintenance is often still kind of an afterthought. But think about this. If you've got an asset that has a 25-year design life, the capital expenditure is fixed, it is what it is. Well, often it would grow. The operational expenditure is 20% of the capital expenditure. So if an asset's 25 years, the operational expenditure is 2.5 times more than the original cost to build whatever it is. And yet it's a secondary thought. I find that alarming. Let's move into solutions. I've got 8 minutes left, Ray. Okay, so I'm going to touch on some potential solutions. So when it comes to digital asset data, I think there's an opportunity to embrace good practice from others. I've probably held up on a pedestal oil and gas quite a lot today, and they do a lot of things well. They've got their own challenges. But when it comes to things like taxonomies, we haven't talked about digital twins today. They've done a lot of good work. So please don't start from scratch and look around at other industries and what they're doing. There's also a whole community called configuration management, which I have to give some credit to my own brother on this, who is apparently a world-leading expert in configuration management. And so there are solutions in other areas. Technology readiness. So when it comes to technology readiness, I think there needs to be better integration again between projects and operations. And understand that if you change the environment and or the duty, you will not get the performance that you expected. It might be better, but it's often worse. Disconnected communities. I think it goes without saying, some of the challenges that we talked around the disconnections between procurement, sales, control, we need to work more closely together. And it might be going forward that there are new disciplines. It might be that universities need to look at the requirements of these new disciplines and indeed apprenticeships and skill and educate those individuals. When it comes to black box decision making, I'm going to propose a solution that maybe the way forward is assisted decision support. We're not handing over to control to the machines. We're going to assist the decision making process. And rather than wait to be able to train multiple failure modes, I'm working on various projects at the moment, there's an opportunity to look at things like anomaly detection. So we've got I hope, lots of good data. Today we are good, we can train an algorithm. Tomorrow we are good, we can train the algorithm. And day after day after day we can build a really strong signature, a database of what good looks like, so that hopefully when bad comes along, it's an anomaly. And in the short term commercially, I think there's a lot of opportunity there, and we need to stay grounded. For obsolescence, it comes back to planning. Maybe looking at criticality assessments with specific emphasis on obsolescence. Think about where you've got old bits of kit, are they critical, and can we plan the spares provision in advance? When it comes to remaining life, I think there's an opportunity certainly to look at stable conditions, maybe rotating equipment that's operating pretty statically, well, rotating at a constant speed for long periods of time, 24/7, fairly intuitive. But be mindful of if conditions change, it becomes difficult for remaining life. And maybe we start to present results in terms of confidence. And we do this all the time in reliability engineering when it comes to probabilistic techniques. There isn't one solution, there's a range of solutions. And so this is the low side, this is the upside, and this is the nominal. And when it comes to specifications, set realistic targets, engage with maintenance engineering, think about what's achievable in terms of the mean time to repair, and what's achievable based on past experience for the mean time to failure, the reliability piece. Just a couple more now, Ray, I promise. When it comes to human reliability, thankfully, our friends in social science have made a lot of progress, and there are solutions out there, a lot of them born out of high-risk industries, nuclear industry. How do we measure performance? What are the factors that impact performance? And most importantly, how do we improve performance? And if you have time, there is a technique called the HART method, the Human Error Assessment and Reduction Technique. And it's a bit like a failure mode and effect analysis on people. And it really is a powerful way of understanding and controlling those error-producing conditions, maybe retiring that bad boss earlier than he planned. Competency, I think we need to sell mechanical maintenance engineering a lot better than we do. We've had a bit of an image problem for a long time, and I think there's an opportunity to say, to school leavers, etc., attract them into the profession. Theory versus practice. Well, for me, one of the opportunities definitely is to improve what we do in terms of professional development and support professional engineers to understand the differences, the limitations and the weaknesses. Resourcing. Let's spend more money, okay? If OPEX is such a massive, or a 2.5% greater than CAPEX, why are we penny pinching in projects, small and large projects, to save a few pounds or dollars on the project when longer term there are some bigger considerations for maintenance engineering and reliability? So some concluding remarks. I'm almost there, Ray, I promise, with 2 minutes to go. To use a phrase from a former mentor and president of the Institution of Mechanical Engineers, good maintenance engineering should not cost you, it should pay you. When it comes to our profession, I think it needs to be better showcased. I think there's a big opportunity to attract new talent into our particular sector. I think there's a big opportunity to influence standards. Nobody wants to, well, a lot of people don't want to sit down in London influencing international standards, but unless we do, we'll not get what we want, even if it's a high-level framework to work to. I think there's opportunities to embrace good practice from others. I've spent my life doing this and working with some really good reliability engineers in the space sector, in nuclear. A lot of my mentors were out of nuclear, and for good reason. They've led the way when it comes to reliability and maintenance, and oil and gas, and the process industry in general. And recognize that maintenance engineering, we've got to support aging assets as well as provide input to the new assets. Ray, over to you.
Would you like to take a seat? We'll let you sit down for a little while. Thank you so much for such a fascinating talk, and I'm sure everyone else will agree with that. I would also like to reassure you, if your bad boss was watching, we all know they won't realise, because bad bosses never know that they are the bad boss, so you'll be absolutely fine on that. Before we get into questions, I just wanted to ask, you mentioned that there's an oil and gas database that you encourage everyone to go and look at. Could you just say that again and maybe spell out what
So the acronym is OREDA, so OREDA. It is available in the public domain. It's not cheap, but it is available. But it is born on the back of a lot of work in the North Sea, oil and gas, over 40 years ago, where there are 2 volumes for major assets. And the way that they gather data and gather failure data for individual equipment types is in my view, best in class. So the OREDA, I think it was a foundation originally, and now there is an electronic database.
Wonderful, thank you. We're going to take some questions from the floor and any that come through online as well. And we would say that there are no stupid questions. We know that people are at different points along this journey, different stages of maturity. So I'm sure if you're thinking it, someone else will be thinking it as well. So please do ask. And to start that, I will ask a question that may be a stupid one. I was really interested to hear you talk about people, and that people are unreliable, and I'm sure we all know that from our own lives, even if not at work. You mentioned the HEART method as being a great way to do it. Can you just tell us a bit about HEART, what that stands for, and what it involves?
The HEART method was developed by a gentleman in the Health and Safety Executive, working predominantly in high-risk industries. It's a method of, well, first of all, identifying for any procedure or any human activity, a generic task. We start with identifying the generic task, of which for probably over 90% of cases that's possible. There are some exceptions. Once we've understood the generic task type, we then identify from a list what are these error-producing conditions. So it might be poor morale, it might be tiredness, working in darkness. There's a whole series of descriptors. And then we calculate the human reliability, or indeed the unreliability. Now the number itself is kind of almost meaningless, because it's also a probabilistic technique. But what it allows you to do is understand what are the factors that contribute to that unreliability and how you can address them. So you've got to be very careful using the actual score on the door, but comparatively the methods are very powerful. And that's not because the method is flawed, it's usually because the people engaged in the exercise don't have the experience if they're reading it straight from a textbook.
Mm-hmm. And would you say that that is, looking at the human reliability, is that a good starting point for people who are going along this journey? Is that something that's relatively easy compared to other aspects to get started upon?
It is. There are around 30 first-generation methods that were developed over 20 years ago in human reliability by psychologists. Very few allow you to start thinking about how you improve the situation. And those that do are very structured. So the HEART method is very similar to another technique that we use to look at the failure modes of machines. So it fits really well with our community.
Great, thank you. I'd like to open up to the floor. Does anyone have any questions? No?
Thank you. Just to get us going, a lot of your references come from high-risk and often highly regulated industries, where the case to make for investment in maintenance and CapEx as well is clearly a bit easier. What do you think about the culture that exists in industries outside those sectors, where the funding and making the case for funding for maintenance is literally a daily fight that engineering professionals have to face?
Very good one, Gary. I mentioned that our work in professional development is often with business schools, world-renowned business schools. Part of the challenge for engineers is their inability to communicate to senior leadership. This is what will happen if we don't do this. So I think there's a piece around communication. I totally accept that for other industries that are not perhaps as cash-rich for oil and gas in a high oil gas price environment, and that there are additional challenges. But I would argue if you're working to tight margins, if you really are struggling to justify those budgets, it's probably even a bigger reason to invest in these areas to ensure that the business is more successful.
Thank you. Any other questions? I mean, I have a whole load. I could talk through the whole lunchtime, but here we go.
Hi, Moray. You talked about digital asset data earlier on.
Yes.
We've been looking at this, as you know, over the last couple of months, and there are no standards for classifying what asset data is. Do you think they need to be in place first before people can really start to use Industry 4 techniques, or do you think people should just get on with it and they will evolve in time?
Yeah, it's a very good one. So those of us old enough in the room will remember PAS 55, which was an earlier standard for asset management, and I was involved in the subsequent standard ISO 55000, and the idea for that was, let's have a standard that considers both physical and non-physical assets, including digital data. The challenge with international standards are trying to reach a compromise globally and then cross-sector, and then the different needs of different businesses. And I don't think we can wait for that. I think there's an opportunity to make good progress maybe internally or through other approaches. I know Francois has some good ideas in this area. And the standards, I think there's more work that needs to be done. But I don't think they'll ever be overly prescriptive because they've got to meet the needs of way too many stakeholders.
Thinking again about data, I had a question when you were talking at the start about the scope of data and what that includes and how often it's about failure rather than success. And I just wonder, do you think there's too much emphasis on failure, or maybe that's not quite the right way of doing it? Do you think there needs to be more emphasis on the success?
Well, this is a great one. So one of the there are specific methods that we use in reliability engineering that actually benefit from success. So we analyse failure data, but we also analyse within that population those that survived, because from an engineering perspective, that influences our outcomes on maintenance strategy selection. So we do use and should use success data in our analysis.
Wonderful, thank you.
Is it time for cake?
We have a question at the front,
Francois,
so we just have one final question.
Thanks, Moray, for this piece of thoughts. It's very interesting. I'll take the opportunity to ask the question before I'm asked questions. So, how do we, on a segue maybe to data, how do we consider now that data should be used to replace or maybe supplement, or is it relevant for assessing the value of the design-led calculation of mean time to repair, mean time to failure? Or is it now the new way, is data the new way to build predictive maintenance?
So I think this is where you and I might differ on this, Francois. So for me, there will always be a need for the definition of a design life in major projects. I think it's the duty of maintenance engineering and operations to deliver on that design life. Often for large projects, the financial memorandum is based on what you promise you would deliver, and it's our job to do that. So I think there's absolutely a piece around better sharing that data with major projects. One of the challenges, that's okay if the technology has been seen before, if that environment is what we've seen before. But with highly innovative projects, that becomes problematic. We can apply stress factors to this. But in terms of the project team, digital data is invaluable, but I don't think we can escape away from what we promise to deliver, and we must ensure that the business generates the value what the project was originally signed off against.